So my group has looked at these defense escort teams, and you're probably wondering what a defense escort team actually is. Well, we've seen them for quite often in escorting high valuable people, things like the Secret Service team. We could think of these Secret Service agents as escorts, and what they're trying to do is keep this valuable cargo safe while they transport. And maybe they're transporting from one location to another. So then that escorting actually becomes more complex because we have to keep them safe at the same time as that we are escorting them. Cool. I'm gonna pull up my chat here, and I don't know if you guys can see that, so I can watch the question. And feel free to ask questions during. We get pretty good at this from teaching. So the other idea is that you don't have to have people being the thing being escort. You could actually have like a convoy of vehicles. So a convoy of vehicles may be the thing being protected, and you need escorts to protect that while it's moving and changing locations. It also, you could think of that convoy as changing shape as well to make that problem even more complex. You could think of a payload escort. So maybe like this quadrotor carrying something valuable, and we need something to escort it to keep it safe while it's transporting. Maybe there are expected issues along the way, and so we just need to make sure that we can intercept those issues so that the valuable cargo can continue to transport. Or we can think of something like this construction site where we have to keep a perimeter about the large equipment that's actually moving and doing its job, and we need to make sure that nothing enters that perimeter around the work site. And what actually inspired me when working on this is actually we spent a lot of time pre-COVID in the airport. And airports can actually be really challenging to navigate with your luggage, maybe with kids. You're walking along, dodging people. Other people like this run right in front of you, and so you're having to change your trajectory in order to modify them. So wouldn't actually a defensive escort team be pretty nice here, so then you can get to your gate on time? Well, we probably actually can't realistically do that. That would cause too much congestion in the airport, but there are circumstances, maybe in terms of this assistive scenario, where we might need some sort of escort to get us along to where we're going. So let me talk with you a second about what are the challenges of this problem. So what's really hard is that we have this valuable cargo that we're trying to move from one location to another, and that valuable cargo itself can actually change trajectory depending on the circumstances. Just like the convoy of vehicles, they may need to go around some piece of road that's been demolished, and so they needed to change the trajectory they'd originally planned. So it's possibly unknown as well. You have a series of teammates. So just like the Secret Service agents, we want them to be able to do that job and do it well and know what each other is going to do. So you have these teammates with limited communication capabilities, so they can't all be talking at the same time. They just need to know what each other's thinking and be able to adjust to that so they can actually do their portion of the task without coordinating with the other ones. And we need to know what the trajectory of the potential threats are in the scenario. So we may have people just walking, and then we may have other threats coming at that valuable cargo. So you have to not only decide when to intercept or what threats to intercept, but you also have to know how to intercept them, how to move to get to the location where you need to intercept, and when to move to that location so that you can get there in time to meet them. So we've worked on this problem. I'll talk to you about our solution and that we have filed with the STC on this. It is me and primarily my master's student or former master's student that worked on this, Arpit Garg. He's currently at Google, and I've had a postdoc and a PhD student work on this idea as well. And we've been well funded for these types of ideas. This one in particular came out of some work that we started with the National Science Foundation, looking at autonomous algorithms for collision-free navigation. What we realized early on is that there's no thing as a sure thing in collision-free navigation when you have stochastically moving obstacles. So this is one way to guarantee safety, or not guarantee, but to get higher estimates of safety when you have escorts going along with you as well. We also have looked at, with the Air Force Research Lab, has been interested in this in terms of large-scale manufacturing problems. So humans in the loop with robots, and how do we maintain that human safety as well? So that was our piece of it, using machine learning for that as well. And we've also looked at we are working with the Army Research Lab at using the Escorts to study human agent teaming. So whether you're the valuable cargo or the Escort team, how do those two coordinate together? So I'm going to tell you about the innovation that we had to come up with. We needed to come up with a general solution for this. And what this general solution really needed to do was to be able to predict the dynamics of these moving obstacles that were going along in this scenario, to identify those threats to the payload. It needed to learn, and it does learn how and when to intercept those threats. And we don't have to tell it. It actually just learns by observing the crowd dynamics and deciding how to intercept them. It has to learn the impact it has on a threat. So it has a built-in repulsive force, but we don't tell it exactly what the force that it has that it can act on those threats. And so it has to learn what that force is in order to figure out how to intercept as well. And it also has to learn how to distribute themselves for best protection. So we don't tell it exactly where to go or what to do. It also has to learn that on its own. And I'll show you some of the results, how this can actually be a very robust solution where we can adapt to the gain and loss of agents automatically. So there are a lot of solutions in this area of how to build defensive escorts. And I'll talk to you about some of those really quick. Some of those solutions include having static agents around that valuable cargo just to defend it. Almost you can think of it like a bubble. If I have enough static agents, I can make a bubble around it. Or I can actually make those agents not just be static, but almost like circling. Again, this kind of bubble idea. This only works really well if those agents can move really fast and have limited energy resources. So we would really prefer if our agents can actually move less and still get the job done. There are also other algorithms coming out of University of Pennsylvania that look at having a region that we need to protect. Usually this region isn't moving because it makes the problem more complex, but they circle around that region. And when they identify a threat, they assign it to a particular agent that will intercept it and decide the shortest path to intercept it. The problem you can see here is that if you have more threats than you have agents, suddenly the algorithms stop working well. So this would be one of the problems with that type of method. And there are other learning methods as well that try to look at this problem, but they usually employ communication or simplified versions of the problem where you only have one threat and limited numbers of crowds around you. So we set up a problem to come up with a solution for this, where we have this transporting payload where it's got to move from some position to another position. And we usually want to keep actually employing the Army's ideas. We actually want to keep a cordon around that safe. So then we know that within that region, we really don't want threats coming in. Then we have obstacles within that space. We call them obstacles just because of the area that we come from, but you can think of them as either the crowd or the threats as well. Those obstacles are moving with very complex dynamics, so they're actually acting on each other. So if one of those obstacles or people moves closer to another, it'll actually repulse it using a social force. That makes the problem a lot more complex as well. And then we have these escorts that have to figure out where they need to go in order to keep that payload safe. There's two different types of events that they watch out for. So they try to stop breaches of that cordon, a breach event being something like this, where an obstacle is coming in that cordon, or a collision event where like an obstacle collides with a payload or collides with a defender, or defenders collide with each other. We don't want that to happen as well. So it's really just taught those three things are bad, and then those two primary things and those variations of collisions are bad. And if the payload is able to progress towards the goal, then it's really good. And we use that to train to learn how to map the sensor input of those agents to the actions that they need to perform to keep that payload safe. Now, this is pretty complex how it actually does that. Underneath it all, it's a deep neural network that takes sensor input, maps that to actions. Oh, I took up the animation here, but it's just going to learn using that reward structure of these actions are good and these are bad. This is the outcomes that I want to achieve. So it pretty much teaches itself. And then we can look inside what that agent actually learns and see something like this. So in this picture, it's almost like we're looking down on that problem that we set up just a second ago, where we have all the positions that the new agent that's coming in, this third agent, where he could go. So we could place him at any position on the board. And the colors indicate where he wants to go and where he doesn't want to go. So red indicates bad places, places he thinks are bad. And blue indicates places that agent thinks are good. So we can see he kind of likes being around the middle of the image, which actually happens to be around the middle of the payload or right near the payload. There's also the cordon region in here as well. We don't explicitly tell him the cordon region, but he seemed to learn it on his own because the blue region right around the payload, around the location of the cordon is where he tends to like to be. And then he sees the other agents in this location and the other white dot as well, and kind of learns that being in that cordon region is good. He also learns that being over here, so if you could see, I don't know if it's going to transmit well over the web, but over here on this region, it's a little bit darker blue. So he learns that being kind of positioned equally distant from the other agents actually really good place for him to be. And he also learns don't go behind obstacles, especially when they're close to the cordon region, because you might push them right into the cordon. So, and then that would be bad for him. So it actually turns out to something like this. Again, we just told these agents what was good, what was bad, set up that complex network, and train them to be able to solve this problem. And you notice them positioning themselves pretty equidistant along that trajectory while the payload's moving. So let's look at how this compares to the those current solutions that we looked at before. So I'm going to compare it to the one that's typically the best, and that's that one coming out of Vijay Kumar's group out of the GRASP lab, a well-known group in robotics. And what we see is that as we expected, as the number of obstacles go up, their results in the orange lines tend to go down, their success rates. So they have more collisions as the number of obstacles go up. Ours stay pretty high because we're only assessing those threats and deciding which ones that we should move towards based on the observations that we're making, not trying to address every threat that's coming at, every potential threat that's coming at us. And it changes depending on the number of escorts that you have. That's the numbers there you see in the plot, that more escorts typically tends to work better. Our solution is actually highly adaptable. So here you see 4 escorts and then 1 drops out. Maybe it lost sensor connection, but the 3 agents don't see it anymore. And so they reposition themselves to cover that 1 agent. And then he comes back and they can automatically reposition themselves as well. We've actually looked at lots of different conditions to figure out what conditions tend to work well and tend to work and we'll talk a little bit about the need and the market potential. We've seen a lot of these applications from the beginning, but what we also see that because of our history in moving obstacle avoidance, any application where safety is important, we're not going to be able to guarantee safety. So escorts are going to help in any condition where safety is critical to the maneuvering of that agent as well. So our current status is we have a current collaboration with the Army Research Lab looking at this human AI teaming for navigation problems with defensive escorts. Sandia National Labs is also looking at using this defensive escorts ideas for aerial defense systems. And we've actually looked at, it's not just general to these planar or 3D agents. They actually can be a manipulator arm where they have to do this interception problem as well. So we've looked at that as well. home. So I think that is everything I had.